assignment page. We have this 8-1 formula that has everything on one page. We have the answers to that worksheet if you want to check that. And then also, let's see, where am I? Okay, the stuff that was due today. This is today. So this is the stuff from Monday. So I made all these videos and we ended up needing them because we did this instead of class. So if you haven't watched those, they'll probably really help you. I've graded some of your homework that you turned in, which is great. Is there anything on here that you have questions about? Like this whole sampling business. You watch those videos from the Pew Research place too, about collecting samples, and hopefully you're seeing a repeated theme that when you're sampling, you need to have randomness in there. Because if you're choosing people, then you no longer have any sort of that connects you from, if it's random, then you can kind of think, oh, well, these people that I chose do represent the population at large. Your goal is a representative sample. That's your goal. You want that spoonful of soup to taste like the whole pot, so you can know what the whole pot is like. What you don't want is a biased sample, which is where the sample is more one way than everybody else is, because then it doesn't tell you what everybody is like. Your whole goal is to find out what everybody's like, your population. So it's kind of the big thought from that. And there's some different techniques we saw in the video, considering the way that you ask questions, making sure that the questions aren't making one answer more likely instead of really seeing what people think. Like if you ask them a question, the mode effect video, if you ask them a question about something that's embarrassing, people are more likely to lie to a real person than they are to an impersonal type survey. And then some people are just more likely to be willing to give you results. So they talked about looking at the demographics of the whole population and then looking at the demographics of the sample and saying, okay, well, we didn't get as many of this type of people as there are in the whole population. So let's multiply these numbers a little bit so that, we were not able to get very many college-age student responses, so we'll just have to count them twice to kind of balance that out. That was one of the videos. We saw that kind of thing. One thing that I would like to point out, probably say it again Monday. There are two definitions for the word mode that we will talk about in this chapter. We watched that mode effects video where they talked about the mode of survey. Like, is this a phone call? Is it a robocall? Is it a paper survey? Is it something on Facebook? Like the way that you collected your data. That's the mode, the method of data collecting. But then we also have the word mode when we're talking about things like mean, median, and mode. Does that ring any bells? Where mode means the most frequently occurring result. So just keep that in mind when you, tonight, or sometime this weekend, when you're doing your prep work for next week. You'll start hearing that word mode in situation number 2. Just know, yep, same word, 2 different meanings, we just have to tell from context what we're talking about. So our next folder of assignments, the things that are due Monday, we have all these optional videos. All of these videos are, I hope, actually just everything that we're going to cover today. Or in an ideal world, everything that we would cover today. Since I'm spending kind of a significant amount of time reviewing, I might skip some of the stuff and just say, well, you can watch that video because it's all on there. So if there's something that is confusing to you from today, you can just watch me talk about it in my dining room on those videos. We're also going to be looking at some graphs and charts and things. I'm going to be pulling up some slides. And these are also available on Blackboard if you need to look at them again. Okay, I think that's all the things on the Blackboard. Okay, so we are going to use the handout, Creating Frequency Distributions. It looks like this. The first frequency distribution that we're going to fill in is a repeat from page 315. And actually, we'll probably want to look at page 314. Because that's where we get the data that we're going to put here. Categorical data is data that we can sort out into different categories that aren't numbers. So the example here is blood types. We've got A, B, O, AB. So to fill out this table, we would just count all the A's, all the B's, etc. This is data from page 314. So does the order matter? No. And it's nice to put it in some sort of like kind of logical way that would make sense. Like if there is some way that kind of seems like, oh, maybe let's put it alphabetical, or we could put it from biggest to smallest, or, but when it's categorical, it's kind of just up to you. I could have started with O. da-da. So when we count them all, 5 of those, 7 of those, 4 of those, and 9 of those. So with this type of data, if we wanted to make a graph, we might want to use a pie chart, or a bar graph. Now, a lot of times you could use either thing. But there are some circumstances that the pie chart fit better than not. A pie chart we really want to use when we're talking about here's this whole collection of things. Here's everybody. Where do they split up? And everybody's in one piece. So everybody only has one blood type. So of this group of people, I might want to make a pie chart because everyone goes in one piece. Of all the people asked, here's how we can easily see from a pie chart. Here's how the number of A types relate to the whole. Now, a bar graph doesn't necessarily need to be a whole. Like, here's everybody. Where do they all fall? Also, it doesn't really need to have everybody just fall into one bar. And maybe we're not even talking about people. Like, let's say we're talking about COVID cases in 3 different states. We might have a bar that says this is how many are in this state, this is how many have been in this state, this is how many have been in this state. We're not looking at all the states in the US. If we were looking at where are all the COVID cases that are in the whole US? Oh look, this chunk of them were in Missouri. That would be like a pie graph scenario. But if it's just like, well, let's compare Missouri with New York and California, we might want to use a bar graph. We're just comparing some things to each other. We're not necessarily looking at the whole big picture, the whole graph. Another example that's in the book talks about, in fact, let's see, do I plan to talk about that? Yeah, I might talk about that. On page 330 and 331, there are 2 charts. On page 330, there's one. On page 331, there's another. And it talks about these 5 different grocery stores. The one on page 330 says, what's your favorite grocery store? So of all these people, they're picking which store is their one favorite. Everyone's in a piece. Whereas on page 331, it's a different question. Which of these have you gone to in the last month? So maybe you went to more than one. So you put a tally here and 2 tallies there or something. So which one's your favorite looks at everybody and sees where they are in that choice. Like, where do you land in your favorite? That'd be a good pie graph. Number 5, which ones have you been to? well, this many people have been to this one, this many people have been to this one, this many people have been to this one. We can kind of compare numbers of visits. That one's more bar graph material, because I may have been to both Trader Joe's and Aldi. And so it's not like I'm landing in one piece of the pie. It's just I'm making those two bars get higher. So other than categorical data, what's your blood type? What grocery store? Those are like categories. We could also have numerical data. And we can get some data for this one from page 318. Wait, nope. Use the data from page 315. No, it's 316. Sorry, that's wrong on the worksheet. That is on page 316. Page 316, we see the record high temperature of each state. Have we talked about this chart before? That is the downside of me making all these videos, because I feel like I've talked about this chart so much. Here we are talking about the chart again. But I think that's all on videos you haven't watched yet. Okay, this is all new. Okay, so in each state we have like what's the highest temperature they've ever had. Let's see what Missouri is. 118 degrees? Whoa! I wonder when that was. Or where it was. Interesting.
Yeah, that's way too hot.
Yeah.
That's way too
Yeah.
hot.
Yeah.
I would have been very much
Word.
It was hot enough as is.
Word. Okay, so when we were talking about the categorical data, it wasn't really hard to figure out where to put the tally mark, because you're either one category or another. But with this one, when you look at this chart, we've got 50 states. They all have these different numbers associated with them. You probably don't want to list every single temperature and write how many states have that exact temperature. That's going to be way too long. I mean, we might as well, that's kind of what this is already, right? So we'd like to group them together. When we group them together, the order is going to matter. I'm not going to make like this category be, 100 to 110, and then the next one is 125 to 140, like, we're going to put them in order. Either from hottest to coldest or coldest to hottest, right? If I were to flip-flop these two, it wouldn't really matter. But here, when it's numbers, it is going to matter. They go in order. And we have to decide how big we want each category to be. Do I want to make each group be just like 2 degrees? Like, I think I marked the smallest one is 100. So do I want to have the first category be 100 to 101? Or do I want it to be 100 to 130? And then the next one, 130 to, whatever. When we're making those decisions, we need to kind of figure out what our smallest is, what our biggest is. When I look through this, I see that the smallest is 100, the biggest is 134. Now, all this stuff that I'm talking about right now, we're moving on to the content from this second video, if you want to rewatch any of this. So when you're trying to decide how big these things need to be, my smallest is 100, my biggest is 134. So I probably don't need to start counting at 50, right? I'm going to start counting somewhere near 100. When you're choosing your categories, ideally you'd have something, I doubt you'd want to get any smaller than 4, maybe 5, number of categories. If your categories are too small, then it's not really that meaningful. But if you've got too many categories, it also ceases to be less meaningful. Like, you want to give as much information as possible without overwhelming the viewer, and then you might as well not have made it. So somewhere in the 5 to 8 range would be like ideal, probably, for number of categories. And then also, it's really nice, if you can, to use pretty numbers. So let's say I wanted to count by 5s. I probably wouldn't want to start with 99, 104, 109, 114. Those,
Absolutely.
that's like, ugh, yeah. Like, let's do 100, 105, 110, right? Pretty numbers. If you can, pick pretty numbers. I think counting by 5s actually is going to work out real great for us. Let's see. That would be starting at 100, 105, 110, 115, 120, 125, 130. The next one would be 135, and we don't need that. 1, 2, 3, 4, 5, 6, 7. That's nice. It's good number of categories. Counting by 10s, 100, 110, 120, 130. We could, it'd just be 4 categories. Probably 5 would be better. Or probably counting by 5s would be better. Having this many is a nice number, as opposed to 4. That's a little small. So we want every single category to be the same size. Don't make this one be like go to 100 to 120 and then 120 to 125. That's misleading when you look at that. You say, oh, that category is so much bigger. Well, it's like it has so many more, the frequency is so much higher. Well, that's because like you cast a wider net for this one and a smaller net for this one. That's very that's a big problem. Keep them all the same size. Then, as far as labeling this, like, what do I put here? I could say 100 to 105, 105 to 110, and so on. I could do that. And some people do. But what happens if I have 105 as one of my answers? Do I put it in this one, or do I put it in this one? If you use your boundary number in 2 places, then you've got to make a clear choice about what happens if you land on the boundary. And we would say, by convention, we're doing this, which says, here's the rule. Even though I have this number right here, if it's 105, it goes here. If it's a boundary number, it bumps up. So this one is technically 100 all the way up to 105, which goes down here. All 110, which goes down here. The reason we might want to do that is if we have a lot of like little decimals. Because another thing you don't want to have happen is to have a piece of data fall through the cracks. If I decide, okay, I don't want to have to explain to people what my convention is. Like, I don't have to explain what happens if it's a tie. I don't want to do that. So let's just make it real clear. Let's just say 100 to 104, and then 105 to 109. Then it's real clear. If it's 105, it definitely goes here. That's great. Except, what if we have a number 104.7? 104.7 is bigger than this, but smaller than this. So look at your data and make your table as clear as possible. Make sure you don't drop anybody. In our data, we don't have any decimals, so we don't have to worry about that. If you did have decimals, then maybe you would want to make this 104.99 or something like that. Just make sure that you've set up your table so that nobody gets left out. Okay, so finish this sucker. Your textbook would definitely prefer you do it this way. But if you look at things online, you might see it the other way. Now, I would like to point out that it is just a coincidence that our smallest and our biggest happen to be boundary numbers. Just coincidence. If my biggest number had been 132, I would still make this go up to 134 so that it was the same size as everybody else. So then we go through and we count them all. I'm just going to go ahead and give that to you. Wait, yeah, okay, so that one I'm not counting. Counting them is one of the biggest places people make errors on tests. Like your eyeballs just jiggle or something and you miss one. You know what I'm talking about. So I would suggest, if you can, just like draw a little tick next to the one that you've already counted or something. Come up with some method to just make sure that you're not missing one or double counting one. This mistake is so easy to make that the textbook makes it. Which cracks me up. So in my textbook, my answer key for this has those numbers. But we're going to look at this data again. When do we look at it again? We look at this data again on page 334, and they have created this table. And they have different numbers than this. They're like, hey, remember those state temperature data? And this was the frequency table you made, except they're wrong. And it's not just that I made the error, because there is a difference between my answer key on one page and what they have on the other page. So, I'll just say, it's really easy to miscount, so be careful. And when we get to that new version, we'll just roll with it. It'll be fine. Okay. They give you some steps for creating a grouped frequency distribution like this on page 316. I think it's super confusing. Just use common sense. Like we kind of talked through it. I think we got it. Common types of graphs for a grouped frequency distribution. A histogram. That's histogram. frequency polygon. This is an example of a histogram for this data. However, that's not right. This one ought to be a little bit higher. And this one ought to be a little bit lower. This is them using the wrong numbers. This is page 334. They've tried to create this chart, and they've gotten some of the numbers wrong, and so then they made their graph wrong. Their graph matches their numbers. So we're now just going to look at their numbers, which is on page 334. A histogram is different from a bar chart, bar graph. Let's see. Here's a bar graph of all the different grocery stores. A bar graph does not have them touching. A bar graph does not have numbers down here. I could mix up the order of these and it would be fine. A histogram does have an order that matters. I can't flip-flop these two bars and it still makes sense. Also, a histogram gives you the boundary number instead of listing each category. So, like this one starts at 100 and ends at 105. That's that first category. And the one next to it starts at 105. It's this category. If we wanted to make a frequency polygon, then I would draw a dot right there in the middle. And then I would also draw dots on the ground in the next empty spot. And I would connect the dots. A frequency polygon is a whole lot like a histogram, except instead of having the bar that goes up to the point, you have a dot and the lines. We've seen that, right? Where do I have page 336? So, remember previously our category went from 100 up to, but not including 105. Now we're using the midpoint number with a dot. This next category went from 105 to 110. Now we're using the midpoint number with a dot. So previously there was a bar that went there. Now it's a dot at the midpoint. Notice these midpoints are all spaced out evenly. 102 plus 5, plus 5, plus 5, plus 5, plus 5, plus 5. And with a frequency polygon, we want to touch the ground on the outside. So, this was my last category. So I count another plus 5, and it hits the ground. Same thing at the beginning. I back up 5, and it touches the ground. A frequency polygon. Do I have one for this page? Nope. On page 337, we see a frequency polygon that they've already made for us that compares final exam grades and overall percentage grades. This graph demonstrates one of the big advantages of a frequency polygon. If you were to use a histogram instead of the frequency polygon on page 337, it would be a mess trying to put two things on the same graph. But when you just have lines, you can compare those two really easily, and it's not like full of two different colors of bars that are overlapping, and that's a big benefit. Another type of graph that is not related to these things at all, other than it kind of looks like this, we put in this little box. A time series graph can be drawn for data collected over a period of time. Let's see, do I have... Okay. Oh, you cannot. There are like dotted lines on these graphs, but we can't see them because of the projector. Anyway, there is a grid here. Here's a couple of examples of time series graphs. This is from page 464. And on number 3, they say, draw a graph for the pairs of data on each graph below. So they want you to look up here and graph this stuff twice. These are the same graph, can't you tell? A time series graph uses time as that bottom row. So we have categorical data that has categories. We have numerical data that has like numbers. Our categories come from numbers, so we have to decide where we're going to draw our boundary lines to create our groups. A time series graph has time on the bottom. So all these different types of data that shows up on the bottom. What stuff is going down here? Is it categories? Is it numbers? Is it time? So here's a time series graph. Time goes on the bottom, and then we're graphing what the average life expectancy is. Both of these graphs are graphs of the same data. Why do they look so different?
Because of the life expectancy, the numbers they chose.
You mean this? Mm-hmm. This one we could use the word truncated. So like if this is the tree and it's growing out of the ground, we're removing like the trunk and just zooming in. Zoom in right here. That's this. That's the zoom in. Whether or not you present your data like this or like this, it gives a really different impression, doesn't it? This one makes you think, things are not changing. This one makes you think, whoa, things are changing so much! But it's the same info. So we need to be careful when we're creating a graph. Am I being misleading or unclear in the graph I'm making? We need to understand this when we're reading a graph. Just because the graph is there doesn't mean it was well done. Or it doesn't mean that somebody was trying to persuade you a certain way, so they set up their graph to make it look like that. You know that phrase, numbers don't lie, but people who use numbers do? That's a great example of this. Neither one is a lie. But just be careful. Probably enough said. Okay. Stem plots. I'll just tell you, I don't like stem plots. I think they're overrated. We'll talk about them anyway. On page 325, number 4, we see an example. How many of you have learned this before? Stem and leaf plot. How many of you have ever seen this used in real life? It's one of the reasons I'm not real big fan. Okay, we'll just zip through it here. So the data is on page 325. Now stem and leaf plot, you do not have to put them in order. I think that's kind of nuts, but you don't have to. It's still correct if it's not in order. So I can just go through this data and say, all right, well, my first one is 38. So for 38, I do 3, 8, 38. So it's like these are all the 10s, and these are all the ones that might possibly go with it. My next one is 41. All right, 41. Then 50. Okay. There's another 50. All right, so let's put another 0 there because it's still the 5, but it's a new piece of data, so I'll put a 0 there. The next one is 92. Then 53. Oh, I'm back here with the 50s. So I'll put a 3 there for 53. 58. 70. Oh, that's a new tens number. Oh, it's out of order, which personally I'm like, I don't like that, but it's okay. It's okay. My answer key is a typo. They have a 1 there. We have another 70. Then 84. 53. 68. Oh, I need to start a new stem. 83. There's another 83. 87. And so on. Are we good with this? And so on. We didn't finish this. So if you're looking at the notes on Blackboard, don't just copy this and say, "Ooh, I'm done," because we didn't finish. But you can finish. That's easy.
a
Agreed.
waste of time.
I agree. I totally agree. 100%. Let's create an anti-stem and leaf plot club. I nominate Dakota the president.
What's the point of this though? Like, how do you get any information for that?
Well, if on page 325 we were to just look at that list of data, you know, it would take us a while to kind of absorb all of that. But if you look at the stem and leaf plot, you might be able to say, oh, there's sure a lot of things in the 50s. It's kind of like a bar graph, actually.
It's kind of like retarded, actually.
True.
So it'd be like, here's how many were in the 30s, here's how many were in the 40s, here's how many were in the
This
50s.
is
And we actually get to see what those numbers are.
so they make a bar graph. This is stupid. This is like the lattice multiplication that I had to learn in like elementary.
Let's just not even go there because
A what?
Lattice multiplication.
maybe if I knew how to do it, I would feel more positively toward it. Okay, we still want to learn, of course we do, we want to learn how to make a pie chart. Like we talked about how, when we might use a pie chart, but let's dig in to how to actually do it. Think a bar graph is pretty obvious, you count how many there are and you make it that tall, right? Pie chart, it's a little more tricky. Let's see, look at this. So let's look at page 330. They have a little pre-made circle for you, so that's a good place to practice it. I think I talked about how to make a pie chart in the first video about, let's see. I think, yep, this first one, if you need to see this again. So we're on page 330. Number 3. So basically, you want the size of your piece to actually match the size of that data compared to the whole. Okay. So we need to know our total. We add them all up. Let's see, there's 80. 80 favorite grocery stores. So that means that 13 out of 80 said that. If we wanted to, we could come up with a percent by taking 13 divided by 80, if we wanted to. 29 out of 80 said that one, 23 out of 80 said that one, 10 out of 80 said that one, and 5 out of 80 said that one. If we wanted to come up with a percent, which you don't have to, percent, on the chart they want you to, I could do 13 divided by 80. I could do that if I wanted to. But that's not really what I need. What I need is how big a piece of pie that needs to be. How big is all the way around? How many degrees is that?
180. Nope.
It does have a 3 in it.
360.
Yeah.
I don't know why I said 180. Yeah.
You know, there are celebrities that make errors like that all the time. My life did a 360! Just totally different now! But if you're 360, you're actually just back where you started.
I think it was because you started drawing the line and I was like, oh, half of it.
Well, so half of it is 180, right?
Yeah. It's like that song that's like did a full 180.
Yes. So then, just a fourth of the way around would be 90, right? And if I chop that one, 45, I think we've got a sense of what these look like, right? Like if someone said, quick, draw me 57 degrees, you might be like, whoa, hold on. Okay, I know what 90 looks like, I know what 45 looks like. It's gonna be kind of in between those. You could probably get that right. Okay, so when we are making a pie chart, we just want to know how big each piece needs to be. And in your book, they're so nice. They've already drawn in little gray lines that are 10 degrees apart. Oh, it's not even. I think they put 0 up here, didn't they?
Yeah.
So you've got 10 degrees, 20 degrees, 30 degrees, and so on. That's nice. That helps you draw it better. You don't have to get out a protractor or anything. So the whole pie is 360 degrees. This is 16.25% of that pie. So in order to figure it out, I could take the percentage and figure out how big a piece it is. Or if I wanted to skip doing the percentage, I could just use the fraction. 13/80ths of 360. Give me the same thing. Either way. So that means that the Publix, is that how you say that? 10, 20, 30, 40, 50, almost 60. Should be about that big. you're doing this on a test, am I gonna get out a protractor and measure? No. But if your pieces are wildly not reasonable, like if you're drawing a 58.5 degree piece and it's bigger than 90 degrees, that's not good. So kind of keep it within what's reasonable. So Trader Joe's. I'm going to skip the percent thing and just do it this way. 29/80ths of 360. 29/80ths times 360 is 130.5 degrees. So from here, 10, 20, 30, 40, 50, 60, and so on. Maybe something like that. I don't have all those pretty lines that you do in your book. Oh wait, that's not Aldi, that's Trader Joe's. Did I say Aldi? Sorry. I read about Aldi and Trader Joe's. Both from Germany, the same German company, and they like split when they decided to go international. It's these two brothers, and they're like, okay, you take these countries and I'll take these countries. And one was Aldi and one was Trader Joe's, except they both wanted to be in the US. So some of their brands are like specific, like some of their brands and like sources go to both of those companies, but nowhere else. Oh, interesting.
I go to Walmart and Sam's.
Also owned by the same company.
Yes.
It makes me uncomfortable saying the name of that store.
We just looked it up and it really is a place and I'll show you all.
Agreed.
Publix, Pudix, whatever it is.
Yep. Yep.
Weird.
Yep. I think we've done all those things we need to do. Let's look at page 342. 342. This is, I think, part of your homework. Whoops! Yeah, you're gonna do 4-2 applications. This is part of your homework. This is not wasted time. None of it is wasted time. So this is not done.
We have a research paper due in a couple weeks in English. I haven't done any of it.
Do you need to include graphs and charts?
No. I really just want to drop out right now.
It's a 5-page persuasive essay.
Oh, it's 5 pages? That makes it
Isn't it?
5 pages is nothing.
I can't even write 2.
You know what Mr. Larson
I'm the
said
same way, I
about
get right to the
Just
point.
include some charts or
Yeah,
graphs, and
yeah.
that uses up half a
the
page.
last 2 papers?
Actually, mine, I could use charts and graphs if mine.
Usually it doesn't count
Last
though
2
toward your
papers
pages.
though, we literally, I
It's
wrote,
okay.
last 2 papers I wrote, he'll give me an F and he'll be like, it'll be a good paper if you redo the whole thing.
Yeah.
I'm like,
Well, at least he's
but you know what
not.
made me mad? Okay, I will say, he did
Ophelia!
motivate me. He did motivate me. My first paper that he did that to me, I was like, oh, he made a little note and he said, if you make all these changes, it could easily be a B paper. And I was like, no, it ain't gonna be a B paper. Like, you're gonna give me an A. So I freaking worked really, really hard on it, and I ended up getting a 96.
Awesome.
So I was like, score. But then
Way
he
to
did it-
bring the good old college try.
But then he did the same exact thing and gave me the same exact score on the paper that I wrote last week.
Well, why don't you do the same thing if that got you the 90
Well,
whatever?
I did. That's the problem. So now I just gotta redo the whole thing again.
Here's the secret to getting 5 pages. Make an outline. Write about everything on your outline and you'll be like, I have too much, and then you can cut it out.
I hate school and I really don't want to go back.
Okay, let's talk about math.
We even choose to come back.
342.
Is that awesome?
We want to just talk about which type of graph would be best. The number of students enrolled at a local college each year for the last 5 years. What type of graph would be good for that? They give you multiple choice here. Bar graph, pie chart, or time series graph. Yeah, because there's time involved. On page 342, any of those others, 1 through 6, involve time? Number 4, yep, so that's also a time series graph. Easy peasy. Number 2, the budget for the student activities department at your college. So, a budget is all the money we have, and we give it to different departments.
Pie graph. No.
Yes, pie chart. If you're talking budget, that's a good thing for, that's pie chart. Budget is pie chart territory. If you're talking about donations from this person or this person or this person, that might be bar graph category. The number of students who get to school by automobile, bus, train, or by walking.
Bar graph.
Bar graph. We talked about 4, the areas of the 5 lakes in the Great Lakes. If you're talking about lakes, it's not like there's some sort of hole that you're divvying up. You're just seeing how much is in each one. So bar. Number 6, the amount of each dollar spent for all these different things by a corporation. So a corporation has this much money, how are they spending it? Pie, yeah. Because we're looking at their whole and how it's divvied up. Great. Good work, team. Lord willing, I'll see you Monday.